Today, we're looking at finding the moment of inertia tensor for any 3D object that you want. We'll use Python for this and do it in two slightly different ways. The first way is a more analytical way where you define the shape of the object that you want to compute the moment of inertia of yourself, solve some integrals, and then get the moment of inertia. The second way is really cool though, and that's where you take a 3D object file, which is available on many websites. You convert it to a voxel-based file, which you can load into Python really easy, and you can compute everything about the moment of inertia in, 6 or 7 lines of code. The reason I'm doing all this is because next week, I want to solve Lagrange's equations for a spinning top. And of course, for a spinning top, the kinetic energy depends on the moment of inertia tensor. And in general, it's not a trivial thing to solve for. So I thought, why not make a video just looking at finding moments of inertia tensors, as that's a really important concept in physics, and then use the information from this video in the next video to focus specifically on spinning tops and finding Lagrange's equations of motion. Anyways, be sure to like and subscribe, join the Discord server, we have the best people in the world there, as a matter of fact, and enjoy.
My phones be flipping, dog.
Woo.
What's going on? No,
That's crazy.
That information is contained in the inertia tensor, bro.
Dang.
Got 6 free components.
Yep.
Describe kinetic energy.
Moving.
Just shut your mouth. That stuff's way too much for me.
Woo, woo.
Now I'll keep talking. You can use Python too.
Oh, yeah?
Download a 3D object, load her in, and compute.
Yeah,
And once
compute
you've
it.
got that tensor, yo, you practically a god.
Woo.
And you can solve equations
Next video.
for a spinning top.
So there's really nothing fancy today in terms of the actual libraries used. We got NumPy, SymPy, Matplotlib, used all the time. Some SciPy for integrating, the double and triple integrator here. And then at the end, I'm going to use pandas a little bit to make some nice looking plots of matrices. Nothing to do with data analysis here, but you'll see that closer to the end. So there's sort of two cases, like I said, we'll be dealing with today. I'll show you the analytical case where you define the shape of the spinning top analytically using a formula, and you sort of write the integrals. You solve the integrals in Python, and it's a little bit difficult because it involves a lot of math. And then afterwards, if you continue watching to that point, I'll show you how to load any 3D object that you want. If you have an object file, there's special file types for this stuff. You can load that into Python, and computing the moment of inertia is really easy. And ultimately, this will be used in the next video, as I mentioned, for computing Lagrange's equations of motion for a spinning top. And in order to do that, you need the moment of inertia tensor, and that's what this video, of course, is all about. So we'll start with the analytical case. And so because the spinning top possesses a cylindrical symmetry, right? No matter what spinning top you have, there's a symmetry in this sort of cylindrical direction. I don't remember the name. But so what you can do is you can define in the RZ plane. R is the function of theta, some sort of curve, and then that curve gets rotated around, and that becomes the spinning top. And before I get into the code here, like for example, this is in the RZ plane, and if I rotate this curve around, of course, I get something that kind of looks like a spinning top, right? Because it would rotate like this, and then it would rotate in all 3D, and you get kind of a spinning top curve. But anyways, we need to define that. So what I do is I define the radius as a function of theta. This is just some angle. And I'm curious from pi over 4 to pi over 2. And I just experimented around with a few functions, and I found that 1 minus pi over 4 plus t to the 1/10 worked particularly well as a function for a spinning top shape. And so, of course, you just define this function. Make sure I import these here. And I define my spinning top shape. And so I define the angle as theta, so I go from pi over 4 to pi over 2, there'll be 1,000 points, and then I define a. Now this is like theta and this is r. I just name these like this so I don't get confused later on. So this is theta and r. And when I plot, right, I plot a times cos theta, which is x, and a times sine theta, or r times sine theta, which is y. And you might be confused by this np.insert. Well, if I look at just a times cos t, right, if I run this code here, I have a bunch of values here, my x values. But what I also really want, I don't want to scroll down all this way for one, but what I really want is I want the point starting here as well at the origin. Because when I integrate, of course, if I don't add this point here, I don't get this straight line and I just get this curve up here. But when you integrate from, calculating the moment of inertia or a mass, you integrate from here to here. So having this line here is a little bit more informative. So I compute A, I get all those things. But if I insert the element 0 at the beginning, all it does is it puts 0 here and then everything else. So I get that first point and then all the other points. And it plots nicer that way. And so I do that for x and y, and I get this nice looking plot here. And so then what I do is, because I have this shape, all the information about the spinning top is contained in this shape. And I can rotate this around and I can get the full volume of the spinning top. Now, I said that I was going to use this later on to solve Lagrange's equations in the next video for a spinning top and create an animation. Well, what exactly is the kinetic energy of the spinning top, right? If I have a volume like this, what's the kinetic energy? The potential energy is easy. It's just whatever the center of mass is times the angle that the spinning top is rotated. So if it's sort of leaning down by an angle theta, the center of mass lowers. So potential energy is really easy for setting up the Lagrangian. But the kinetic energy is more tough. And the kinetic energy of the spinning top is 1/2. This is the angular momentum, omega t, I omega. So I is a matrix here, and I expand it like this. And so finding omega, I'll do that in the next video. But what you really want here is all the coefficients of this matrix. And so what I'll show you in this analytical part of the video, for a cylindrically symmetric volume, how to find this matrix here. And so first of all, note that the matrix is symmetric. So there are 6 unique parameters, right? Because Ixy is equal to Iyx. So really I only need the top 6. And what I want to do here is I want to find Ix, Iy, and Iz. Now, there's some more symmetry arguments here, right? Because it's cylindrically symmetric, Ix and Iy, supposing this is the z direction, these are going to be equal themselves, right? So if I find Ix, I know Iy because of this symmetry of the spinning top in the xy plane. So there's these two. So once I find one, I have the other. Iz I need to find on its own, and I'll show that these cross terms here through a really simple argument are all equal to 0. So really you have a diagonal matrix for a cylindrically symmetric volume rotating. And another thing, right, there's a lot of stuff that sort of adds up here. We want to find this in terms of dimensionless quantities. And if you've ever looked at moments of inertia, you'll see they're always expressed as like I is equal to something times mr squared. So like the moment of inertia of a sphere is equal to 1 or 2/5 mr squared, for example. So we need to define a characteristic mass and a characteristic radius here. And then what we'll solve for, instead of solving for I, we'll solve for I over mr squared. And we get a numerical value there, something we can deal with on a computer. But of course, that adds an additional complexity to the problem. And that's stuff that we'll go through here. So let's find the moment of inertia about the z-axis. Well, Iz is equal to the triple integral. We have the mass density here, which will be constant. X squared plus y squared, that's the distance squared to the z-axis, right? If I have my top like this, there's the z-axis. X squared plus y squared gives me the distance. So that's sort of how you write this. For Ix, it would be Iy squared plus Iz squared, the distance to the x-axis. So this is the integral we need to solve. Well, I can write this in terms of integrating over z, r, and phi here, right, in cylindrical coordinates. Now, I know phi is from 0 to 2 pi, so this is easy. We need to be more careful about r and z, so I haven't written them quite like that yet. And because there's no phi dependence anywhere else, I just can do the integral over phi, and I get 2 pi times the integral over r, integral over z, of rho of rz, r cubed dr dz. And now this is eventually going to be constant, so really it's a simple integral. The tough part is finding the bounds. Now, in the RZ plane, we can also convert to polar coordinates, which is going to be easier in this case. So what I do is that I find capital R is root r squared plus z squared. All I'm doing is I'm converting to polar coordinates in this plane. So I define a capital R, which is r squared plus z squared. This is the dimensionless one, by the way. And I define an angle, I forget what it is, but it's the angle in polar coordinates in this RZ frame. Really, this is actually spherical coordinates, but I thought it would be easier to talk about it this way. So r is root r squared plus z squared. Beta, which is the angle, is tan inverse of z over r. That's how you define the polar angle in a simple way. And I let the edge of the curve be given by capital RE of beta, right? Because beta is the angle, right? So RE of beta would be this curve here, for example. And then I integrate from 0 to RE of beta when I'm integrating, so I sort of cover this. That's why I added this line here, because it was more informative when you integrate over from like origin to this point. So the edge of the curve is given by RE of beta, and so I can write the integral as I is 2 pi, the integral over beta is the angles, and I go from 0 to RE of beta, so I'm integrating from 0 to this curve, and then I integrate over all beta, and I just plug everything in. So r cubed, right? I can solve for that in terms of, right, little r is r times cos beta, right? Little r, x, it's kind of like the x in polar coordinates, is capital R, the radius, cos beta, which is the angle. That's why I substitute that in there. So I substitute that, and then dr dz, I convert, this is like dx dy, converting to polar coordinates, dr d beta, and I need to add a another factor of r there. So this is my new integral here for the moment of inertia. This should be iz here, so maybe I can add that, iz. And so I have this integral here. And now I want to convert it into a dimensionless quantity, right? So I let r prime is equal to capital R over r naught. So that's like this radius here divided by r naught. That's the characteristic radius of the problem. And I let rho of r equal to rho naught. So that's some mass density times h of r beta. H is just some function that's dimensionless. And I like the way of writing this mass density this way. You have rho naught, which is an actual thing, and then a dimensionless function. This is just expressing it in a convenient way. And so I divide by everything, right? So I divide by rho naught r naught to the 5, substituting everything in and dividing by this quantity, and I get 2 pi integral over beta 0 to r prime e of beta. This is the dimensionless radius here. And I have h and then r prime to the 4 cos cubed of beta dr prime d beta. And this factor, of course, comes out from, I have a bunch of terms here when I substitute everything in and I divide by them. I encourage you to really go through that slowly and actually write it out because this is sort of complicated, what's going on here. Now, we really want I over m r squared, so we need to find the integral for the mass as well so that we can divide things and get I over m r squared. So the obvious thing to do next is to find an integral for the mass. So the mass is easy. It's just the integral of the density over all the volume. Like before, because there's no phi dependence, it's 2 pi, the integral over beta. By the way, beta, like I said, is from pi over 4 to pi over 2, right? That's beta. That's the angle in this RZ plane. So beta goes from pi over 4 to pi over 2. 0 to RE beta, the function that I defined, and I have the mass density, and this is the volume element here. And so dividing all the terms, I get m over rho naught r naught cubed is 2 pi, same bounds, and substituting all this stuff in here, I get this here as my integrand. So this is the new integrand. And what I do is I have this expression here, I have this expression here, and I want to find I over m r squared. So I take this, I divide it by this, and I get exactly iz over m r naught squared. This integral up here divided by this integral down here. So, I've gone through the math pretty quick and the substitutions and stuff, but it's stuff you can write down by hand and confirm. And so I define the appropriate integrands here, right? So that my numerator integrand is just if h is equal to 1. So I have a isotropic mass. There's no change in mass. It's a uniform substance. Then I just have r to the 4 times cos cubed of beta. That's my integrand up here. And the denominator is just r squared times cos of beta. So I define my integrands. And I want to make sure that this is the correct formula, so I test it first with a sphere. I have a sphere, h prime is 1. It's just a uniform density sphere. Beta goes from negative pi over 2 to pi over 2. So if I were to plot it in this plane here, it would go like this, right? So the sphere kind of comes down like this. And I'm finding the moment of inertia about the z-axis of this sphere. And I know that that's 2/5 mr squared. And so what I do is I solve for, really what this is iz over mr squared. This is what this formula represents. So I find the numerator by doing a double integral of the integrand function for iz. So this is the way that you set this up in Python. I define my integrands and then I do my integral. Double quad comes from scipy. I imported it above. So my integrand, the first variable here, beta, it's actually the second in the function, how it's defined. So if it's second in the function, it's the first thing you put here. This goes from minus pi over 2 to pi over 2. And the radius is just from 0 to 1. Now, you might be wondering why I'm putting lambda x and lambda x. That's a function. And when you're doing a double integral in Python, you always need to put a function as your next arguments here. So this is the bounds for the first variable. Bounds for the second variable needs to be expressed in terms of a function. This is because in general, this re prime of beta for our case does depend on beta. So this would actually depend on a parameter. And I take 0 because it returns both the integral and the error. And I only want the integral. I don't care about the error here. So I get the numerator and denominator, and then I get iz over mr squared. And I solve this, and I get 0.4, which is 2/5. So the formula here is correct. And this is more general than a sphere. And so now I put my function, right? The uniform mass is h prime equal to 1. Beta goes from pi over 4 to pi over 2, as you see on this plot, pi over 4 to pi over 2. And I express my particular function, which is f of x. So beta goes from pi over 4 to pi over 2. The radius goes from 0 to f of x, which is this function here. So I'm going from pi over 4 to pi over 2 and 0 to this function. And remember that I've already done the integral over phi because there was no phi dependence. That's why I could write it as a double integral and not a triple integral. And so I do this. I get my numerator, denominator, same as before. Only difference is this function here. And I get iz over mr squared, this value here. And so I've confirmed it with the sphere up above. And I get the value below. Now, the moment of inertia about the x and y axis is a little bit more complicated because we don't possess the same symmetry. X-axis, remember, could be sort of, you could think like this, and we want to find the moment of inertia as the top almost like tilts towards the x and y axis. And we don't have the same symmetries here as above. So Ix is this is the distance to the x-axis, z squared plus y squared. So that's the distance I am from the x, the big x-axis in the plane. Like before, it's an integral over z, r, and phi goes from 0 to 2 pi. The issue now is that, well, z is fine, but y depends on phi because y here, y is r sine phi in cylindrical coordinates. So I now have a phi dependence in my integrand, and my integrand is r d phi dr dz, so I can't remove the phi integral. Like before, I convert the rz plane into spherical coordinates, or polar coordinates, sorry, so that I have this capital R as r squared plus z squared, and beta, like defined before, the edge of the curve like this, and my integral goes, the integral over beta, which is, in our case, pi over 4 to pi over 2, integral to re beta, 0 to 2 pi of everything expressed here. I do the dimension, make everything dimensionless like I did before, so r prime and rho like this, and I substitute that all in, and I divide, and I get this here for ix over rho naught r to the naught to the 5. I'm going faster here because it's basically the same thing. And of course, I can't do the integral over phi because I now have this sine squared phi factor as well. We already know the mass. I found the formula for the mass up here. It's just this expression here. And like before, I divide this by the mass term. And I know that Ix is equal to Iy as well. And so Ix over mr naught squared is equal to Iy over mr naught squared. And it's this formula here divided by that integral that I found above for the mass, right? And so I just define a function integrand Ix. Now it depends on phi, which is my first integrand, comes first. R here, so that's my integrand over r, dr. And then beta, integral over d beta as well. And I define my integrand just as it's written above with h equal to 1. And so my test case is a sphere with h prime is 1. Beta goes from negative pi over 2 to pi over 2. Like before, it's the sphere, except the sphere is not rotating about the z-axis, it's rotating about the x-axis. But that's the same, so it's also 2/5 mr squared. So my numerator is a triple integral. This is the integrand, of course. So like the first case, negative pi over 2 to pi over 2 corresponds to the last argument beta here. Then r goes from 0 to 1. It's just a sphere of radius 1. Or that's the unit length divided by, because remember, r naught is the characteristic length here. And then the last function takes in two variables, right? Because in general, this outer integral bound can depend on all the things inside of it. But here it's just constant. It's just 0 to 2 pi. That's the integral over phi, of course. Sorry, that's the inner bound. The inner bound can depend on everything. The outer bound, in general, can't. And so this becomes my integral here for the numerator of just the sphere. And I have, of course, my function like this. And all the bounds are adjusted for the sphere. Denominator is the same as before. I solve this. And once again, I get 0.4, 2/5. So I've solved for the sphere correctly, and I've done a consistency check. And this is important when you're writing this sort of code. And now for our curve, we have a uniform mass, so h prime equals 1, and beta goes from pi over 4 to pi over 2 like before. And so I have this new integrand, goes from pi over 4 to pi over 2. My r integral goes from 0 to f of x, which of course is the function that I've shown many times above. And then finally the integral over phi here goes from 0 to 2 pi, and it doesn't depend on other parameters in this case. And a denominator, like before, is just the mass of the curve, which goes from pi over 4 to pi over 2. And it's just a double integral. We solved that above. And I can do this, and I get the following value here. So now I want to show that the off-diagonal terms are equal to 0. And I'll do an example with ixy, for example, and this argument holds for all the other cases as well. Well, I have the triple integral of rho xyz, xy dx dy dz. This is like the formula for the off term. So if I have xy, this is equal to xy. If I have yz, it's equal to yz here. And so I can split this integral up as follows. I start with my integral over x, and I bring everything that's a function of x inside that integral, so that includes this term x here. So this goes from, in this case, right? So you can think of this as like x, like this is r, but think of like a snapshot in the xz plane. I go from, this curve here, which is a function of z to some extent. I mean, I might have this split it up into two functions of z, and it goes from negative some function of z to positive some function of z. So my integral over x, negative some function of z to positive some function of z, and that's how I'm integrating over this particular x plane, right? That's my integral over x. So that's what I mean when I say I go from negative some function of z to positive some function of z. This mass density times x dx. But rho, if I have a cylindrically symmetric object, rho should be even in x. In other words, if it's a mass here, it's also the same mass here, because I rotate everything around. So it should have the same mass density for a particular value of x. This means that rho of x, y, z, x is an odd function here inside this integrand. If this is even in x and this is odd in x, I mean, forget about the fact that there's y and z. This is an even function in x. And so the whole thing here is an odd function in x. And I have an odd function integrated over a symmetric bound. And that's exactly sort of what you see up here, right? It's a symmetric bound that I'm going sort of back and forth. If this thing gets rotated around, then this gets mirrored here as well. Symmetric bound, odd function that I'm integrating here, because I multiply by x. And so this term in here is equal to 0, and so everything is equal to 0. And you can try this with any of these terms, and all 6 of them are equal to 0. So that's really handy. We have a diagonal matrix in this case. So the conclusion for analytical is that our matrix I over m r naught squared is given by, and I just create a diagonal matrix of these elements, and I get the following matrix here. So these are my terms above. This is ix and iy, and this is iz. So it's pretty mathematically intensive, I would say, to compute the matrix this way. So in the next video, of course, I'll show that the angular momentum vector is equal to this, and there's some vectors given by this diagram, and then you can solve for Lagrange's equations with phi, theta, and psi here, which are given by this diagram. But that's for the next video, of course. And now I want to get into taking any arbitrary 3D object and solving for it that way. What I'm about to show here works for any voxel-based image, voxel being like individual points or like cubes or whatever. And so generally when you have a 3D object, it won't be given like that. It might be given as an STL file in this case. And so what you can do is you can use the website that I'm showing here, and you can upload an STL file and it will give you a voxel file. And the nice thing about the voxel file is it returns the coordinates of all the cubes, right? So you have like a discrete approximation of a 3D object. So I converted it to a text file on that website that I've stored in a particular directory on my computer. And I load these coordinates, and I just do some switching here to switch the, I think it's the y and z axis because they're flipped in the way I would like them. And then I normalize the coordinates, and I get some x, y, and z values. So I have all the x locations of my coordinates and the corresponding y and z locations. And so if I make a scatter plot, all the points will line up into this 3D object. And so what I do is I adjust it so the spinning top is centered, so that xy equals 0 corresponds to the center of the spinning top on the z-axis. And I make it so that the very top of the spinning top is at z equal to 0. And so that, or the bottom of the spinning top is at z equal to 0. And that just makes everything easy for the computational purposes. So for example, if I were to plot this right now, if I were to just plot this as is, you can see that things aren't quite aligned. For example, the top of the spinning top is at like 0.4, 0.4. This is at 1. I want this top of the spinning top to be at 0, and I want the center to be at 0, 0. So I make some adjustments to x, y, z by taking the mean and y of x and the max of z, and I create this point here. And I take all my coordinates all together and I subtract this point. So I'm shifting the spinning top to a new centered location. Again, think about this for a little bit. I do for the mean of x and y and the max for z, and I get new coordinates. And when I plot it like this, you can see that the center of my spinning top is at 0, 0, and the top of it corresponds to z equals 0. It is upside down, but it doesn't matter for computational purposes. And so the moment of inertia is really easy about its center of mass. For example, Ix is equal to the sum over k of little mk. So each one of these points has its own mass. And then yk squared plus zk squared. This is the distance to the x-axis. Sort of like before, you can see the similarity between the discrete and the continuous integral version of these. And of course, these are the off terms. And I'm going to show that these are equal to 0 because this particular 3D object, of course, is cylindrically symmetric. But again, like before, we're really interested in I over mr naught squared. So we need to divide by capital M, which is the sum of all the little mk's, right? That's what the total mass is. And furthermore, since what's shown in the 3D plot are things like xk prime is xk over r naught, right? So I'm assuming that a unit of 1 here corresponds to r naught. I also want to normalize divide by r naught squared as well. So Ix over mr naught squared is equal to this. The sum over k, mk, yk prime squared plus zk prime squared. I'm saying what you do see in this plot already is xk prime, yk prime, and zk prime because 1 corresponds to a unit of r naught on this plot, which would be like the height, for example. R naught is not the radius in this case, but it corresponds to some dimension, which in this case is the height of the spinning top. So if we assume the objects have the same density everywhere, then all the mk's are just equal to m, some little number m, right? They're all equal. And I can factor that m out of both sums. And the bottom sum is just the sum over k of 1, right? So that's all the masses, and that's just equal to big N, where n is the number of points in the object, right? So this formula, Ix over mr naught squared, is this sum of these terms here. Really easy. I have access to these arrays, and then n is just the length of these arrays. And so I don't need to show this here. And so what I do is I compute the components of the matrix. So n is chords.shape 1. This is just the number of points in the array. And Ix is really simple. You just sum the coordinates. This is y squared plus z squared. I sum them all together and divide by n. That's exactly what this formula is here. Same thing for y and z. And the Ixy, like before, is these xk times yk, right? So I need to do all the xk's times all the yk's. What I'm doing here, divide by n. Same thing with yz and xz. And like I said, because it's a symmetric 3 by 3 matrix, there's 6 quantities that are unique because they're mirrored across the diagonal, of course. So I can find all these, right? Really simple. All I did was I loaded my object. I adjusted it so that it was centered. I have my arrays of all my coordinates. Once I have all those arrays, I just plug them in like this, and I have all 6 moments of inertia. Very simple. And I can get the matrix. And you can see that on the main diagonal, they're all non-zero. And off diagonal, they're really 0, right? These are really small numbers. And so that's why I imported pandas, just to show in terms of coloring here, is that if you look at this matrix, you can really see what's going on here. So the x and y moments of inertia, in other words, remember x and y is like if I were to take this and tip it right over, this is like the tipping of the top, not the spinning of the top. The spinning of the top, the z1, has a really small value. It's got a lower moment of inertia like that. But if I'm taking my spinning top and I'm tipping it over, there's a much larger moment of inertia. So I showed that x and y have the same moment of inertia. And that's also what I showed analytically as well. Remember, this is all numerical. I showed that the off terms are all 0, so I've confirmed what I showed above. And I have also showed that the z moment of inertia is small. All the code for this video is on my GitHub. There's a link in the description to that. Also, remember to join the Discord server as well. There's plenty of nice people to talk to. We've engaged in various conversations about different projects that people are working on and all sorts of stuff. So link in the description to that as well. Subscribe, and I'll see you next time.